I fixed the, you know what, I can check one thing, hang on. Okay, I fixed my geometry sketch pad document here, so let's take a look at it. So what we want to do here with a parabola, turns out this ends up being a parabola, but the way this is defined.
Please excuse this interruption. I have a bus that's just arriving with about 20 students on it, so please excuse their tarding. Thank you.
The way a parabola is technically defined, at least in terms of analytic geometry, is it's the locus of points, and that's a word I want you to be a little bit familiar with. It doesn't really show up probably in our book or in any high school textbooks, but it's one that you guys need to be familiar with. A locus is defined as a set of points in math that fit certain rules, right? So there's gonna be some constraints on this set of points, and whatever that set of points, we want the set of probably an infinite number of points that are gonna match these constraints. So for a parabola, all it is this. We want the set of points that are equidistant from some point in the plane, which we're gonna label the focus, and a line, which we're going to call the directrix. And so this distance has to always be the same as that distance, right? As we talked about yesterday, the distance from a point to a line always implies the perpendicular distance, right? That's going to be the shortest distance, okay? So watch what happens here then if I drag this point. Notice you can see up there at the upper left that the lengths of AC and BC stay the same the whole time, right? And you can see that the measure of angle EBC is always right, okay? So in order for that to happen, you can kind of get an idea what that shape is going to have to be. I mean, we can see that it's, that it's parabolic, right? And if let's see if I can do this now. So if I go that guy. There it is, right. So that's the locus right there. Did you see what that command was? You guys have to play hoops? Yeah. All right, good luck.
We'll be back. We just have to go do something for it.
Oh, is this for the orange app? Oh, I got you. Okay. So you notice what I just did there? I just look at the button I just hit. I hit the button locus. So this is the locus of points that are defined that way, and look what it looks like. It's a parabola. Okay? So that's the set of all those points that meet that description. That's the shape that they take. Let's talk about then how we can derive this equation. Okay, so I think maybe I didn't have enough time to really make it clear what was going on here. So this is just the x-axis, and this is the y-axis, and so that's the origin, right? We're going to take a situation here where this point right here that we call the vertex, that's kind of the special point on the parabola. That's like sort of the point of the parabola, right? If we were to draw, notice that the parabola has what kind of symmetry? How would you describe the symmetry of a parabola? Folding symmetry or line symmetry about what kind of line? About a vertical line, right? So this is the axis of symmetry. Everybody agree? So then could we define the vertex in terms of the axis of symmetry in the parabola? Yeah, okay, I'm seeing this universal symbol for where they cross, I'm assuming, right? So the intersection of the axis of symmetry in the parabola is at the point or the vertex. So on our picture then, let's let the vertex, that one unique point on the parabola, sit to start with. Let's just put it in a convenient place. We'll put it right on the origin, right? And so then if we define this distance between the vertex and the focus, which is also going to be the distance between the vertex and the directrix, if we define that as P, let's just call that P, and that's gonna be something that could vary, right? We could change the value of P and probably change the parabola, right? If we call that P, then the coordinates of this point where the focus would be is just gonna be over 0 and up P, so 0P, right? Okay, and then the equation of the directrix would just be the line y equals negative P. Everybody agree? Okay, now we're trying to come up with a set of points that, an infinite set of points, right? And we saw what that looked like. The set of points is just that set right there. There's the locus, right? So if we want to represent a random point within that locus, what coordinates do you suppose we should probably give it? The location of the focus we made 0P. Is P a variable? Okay, I mean, it can vary, right? But it's not a variable. It can vary, but it's not a variable. What in the world does that mean?
Because like it always has to be one number, we just don't know which one it is.
Okay, for a given parabola, once we decide, okay, we're gonna have a parabola we're gonna look at and study, then the value of P is gonna be the same for that parabola. It's part of what defines that parabola, right? There are an infinite number of different parabolas, and so therefore there are an infinite number of possible different choices of P. Okay, but what this is really called technically is a parameter. And that's a word that comes up a lot in math, so I want to make sure everybody understands kind of the flavor of what that means. So it's a parameter is a value you can dial in to select an individual trajectory of something, right? So there's an infinite, in math and calculus, we'll come to call this, thank you, you're probably on that bus, I'm guessing. In calculus, we'll talk about this as a family of curves. So there's an infinite family of curves, of parabolas, that would even be centered on the point 0, 0. And as you change P, those curves are going to change slightly, right? And so they might look, if I were to draw all of them, here's one of them. Another one might look like, let's say it might go maybe more like that. Another one might, but they're all going to look basically the same, right? This family of curves. But dialing in a value of P is going to dial in exactly one of those. Does that make sense? Okay. So it's not a variable. It defines individual parabolas, right? So, but for each individual parabola, it's going to be fixed. Okay, but what about the coordinates of this point right here? Remember, that point is a representative point. There are an infinite number of points in this locus of points that come together to form a parabola. I chose P here because that's a parameter, right? But what the coordinates of what we're now calling point C up here, those have to be able to vary even for a given parabola, right? That truly is a variable, isn't it? Because it could be there, or it might be up there, or it might be right there, right? Those are all part of the same parabola. So what coordinates do you suppose I should probably give to C then? X, Y, yeah. Because X and Y are going to be variables even for a given parabola. You see the difference? Okay. So if we go back to this picture, then that makes sense, right? Those are going to vary. So if we're going to say the coordinates of a given point in this infinite group of points, set of points are X, Y, then that defines this point down here, the point that's vertically aligned on the directrix, as being over X and down P, right? Everybody agree? Okay. So how are we going to do this then, right? We're just going to go back to our basic definition of the locus. It's the set of points that are equidistant from the focus and the directrix. And we're going to use that statement to build the equation of a parabola, right? All we're really going to say is this distance, right, has to equal this distance, and just go from there, right? Questions? Does that make sense? Okay. Let's just see what that looks like then. So let me move this up where we can see it a little better. Okay, so what's that look like? So then, I probably should have made this, here, I'm gonna kind of color code this a little bit. So let's say that this distance right here, we're gonna call that segment red. By just using the distance formula or the Pythagorean theorem, right, we know, let's just fall back on the distance formula. We all are familiar with that, right? We know the distance formula is just distance equals the square root of x2 minus x1 squared, just change in x, right, in a right triangle, plus y2 minus y1 squared. Well, in this case, we'd maybe call this x1, y1, and this x2, y2, right? And just apply the distance formula. So then does everybody see that this becomes what we get from the distance formula when we use these two endpoints? Just plugging them in, right? We get x2, right, minus x1 squared plus y2 is this guy minus y1 squared, right? No big deal. Okay, everybody see that? Okay, and this distance right here, let's make this one green, how about? Is going to be that guy. And I wouldn't even have to write it in that complicated a way, because we can see the x coordinates are the same, and so really the distance is just y minus negative p, right? I could even just write it as y plus p if I want to. Okay. If we don't want to use the whole distance formula. Make sense? Question?
So this equation is the equation that makes a parabola.
Right. Did you see why though? Right, because it has to, because all we're doing here is we're saying the red distance equals the green distance, right? But we've kept it general, right? We've written this in terms of the parameter p, which is going to be define the parabola and the variables x and y. Yes?
What are a method for solving this equation to get the vertex of the parabola is not zero zero?
It would. You're right, and it's a good question. What's that going to do to things? It's going to make them a little bit more complicated looking, because then instead of starting at 0, 0, we'd start at hk, right? And so that would make this point up here h and k plus p, right? And it just makes this process look a little bit uglier, right? But we could have done that very easily. The alternative is, which is what we're going to do, let's just solve this in general for a parabola with a vertex at the origin, and then just translate it. Right? We'll take our result and say, well, what if we just translate it to HK? HK could be anything, right? And that'll work too. It's just the algebra looks a little less messy if you do it that way. But either way would work, okay? So if we just do a little simplifying, that's all we're doing here. X minus 0 is x, right? And everything else stays the same in this guy. Over here, x minus x is 0, so that one just goes away completely. And so we end up with the square root of y plus p squared. Same thing, just y plus p, right? We could have just left it like that too if we wanted to. And then when we square both sides to get rid of the square root, here's what we get on the left side. And here's what we get on the right side. Either way, whether we did it the way I've got written down here in black, or if we just had started with y plus p, if we had just made it simpler, the distance, and then squared that, either way you get y plus p quantity squared, right? Make sense? Okay. So once again, don't lose sight of what we're doing here. This is really cool. This in math, this is one of the awesome things about math is you can start with a pretty simple idea and just define it in terms of mathematical relationships, right? Equal distances. Well, just write those distances down mathematically and set them equal and go, right? Just do algebra until it looks good. What could we do here? Well, we could expand out the y plus or y minus p squared. Right, that's no big deal. If I do y minus p squared, what is that going to be equal to? What's that equal? Okay, y minus p times y minus p. Do you guys know from Algebra 1, do you know the expansion for that, the shortcut? It is, it's FOIL, but have you ever learned this? And if you haven't, it's no big deal. Have you ever learned this one, where if you do a plus b quantity squared, it's just a squared plus 2ab plus b squared? You guys know that, right? Probably saw that before. Okay, so then all I've got to do here, that's a and negative p is b, right? So we just get y squared plus 2 times y times negative p, or minus 2, I'm going to call it 2py, and then plus negative p squared is just p squared, right? Everybody see that? Oh, there it is, right there. Okay. What about y plus p squared? Same thing, that just becomes a plus. There it is, right there. All we did is expand those out. Okay. Why might we have done that? As you get better at algebra, you'd probably look at that and say, okay, this looks pretty ugly, but if I expand this out, looking ahead, I'm going to have some common terms that are going to go away from both sides, right? They're the same on both sides, so I can subtract it away from both sides. And if we do that, look what happens. All that stuff goes away, and we get a pretty simple result, right? The last thing we could do, recognizing that we have like terms there and there, we can just combine them, right? Let's just add 2py to both sides, and we get this result. That's good. That's a pretty compact result, isn't it? Now think about that. Look where we started. You know, we started back here with this idea that the red and green distances are always the same, right? And look where we ended up. That's pretty good, right? The last thing we've got to do is to make this completely general, is address the issue that Tyler brought up, that this is centered on the origin, and we don't want to just find the general equation for parabola centered on the origin. We want to be able to place the vertex any place, right? And so the last step for us would be to just do this, just to translate to the point HK, which just means that x is going to turn into x minus h, and y is going to turn into y minus k. When we do that translation, which just means that x becomes, so this is what it ends up looking like, right? When we make that transformation. And we end up then with the completely general equation for a parabola, right? I think that's pretty cool process. We can do that. We end up with something like this, all right? And from here, in the future, we'll explore how we could write this in different ways, right? We could write this parabola. This is what we'd call standard form in analytic geometry. In algebra, sometimes we'll choose to write this a little differently, right? And sometimes we want to write this in the form, well, I won't go into it now. I don't want to confuse the issue. But we could choose to express this differently. Just like we write the equation of a line, lines we can write in a couple different ways depending on the context. Like we could say one form of a line would be slope-intercept, right? We could also write a line in standard form, right? Algebraic standard form. And why do we do that? Well, like later on when we solve systems of linear equations by using a matrix method, it needs to be in standard form, okay? All matrix math requires this, but that's more convenient for us when we're graphing stuff, right? So, you know, just depends on the context. Questions on that? That make sense? Kind of, sort of, maybe. You might have to go back and take a look at this, but you guys, I want you to. I wouldn't be so worried about just any old Algebra 2 class, but for you guys, this is really an important process. I want this to hit home and understand, you know, where we start with this, with the definition of a locus, and just, you know, come up with a general equation from there, okay? All right, so next issue then. Let's take a look at some, and one last thing. Okay, so we did this for vertical parabolas, right? But if we're just talking about distances, about the set of points equidistant from a line and a point, we could just as easily have made the line and the point aligned differently. We could have had the line be vertical, that's what I mean by this. So there's my directrix. And let's say here's the focus. And so then this would be the set of points, right? We could have had it aligned horizontally instead, right? Well, how do we do that? Remember, we have a process for this, right? If we talk about an inverse function, what does it mean to do an inverse? Inverse just means that you're going to switch the x and the y, right? What did that do in terms of the graphs? Inverses had what kind of symmetry? Do you remember? So let's start off, let's just say hypothetically that this is going to be our, say that that's our first parabola, okay? If we take the inverse of that, what's it going to look like? Okay, it's reflected over the line y equals x, isn't it? So there's the line y equals x. So we can either just reflect it over that. Do you remember the two-step simplified version of that? How I showed you how you can, because that's kind of hard to do sometimes, to reflect something over a diagonal line.
Oh, you say like rotate it then?
Yeah, good. So we rotate it 90 degrees counterclockwise and then flip over the y. Okay, and if we do that, look what's going to happen. This is going to go from there down to kind of like that sort of, right? That's the rotation. If we reflect that over the y-axis, I didn't draw that very well, but you get the idea. It looks something like that. Pretty bad parabolas, but, right? Okay. So then that creates our horizontal parabola. Well, if that's how we do it, oops, then really all that's doing is just, what we did to accomplish that by taking the inverse is just switch the x's and y's, right? So this x is going to become a y, right? This y is going to become an x. And then h and k really get switched too, don't they? Right? Because if you think about this, the coordinates of the vertex, if the vertex here was at the point hk, well then the vertex, I really didn't draw that very well, but the vertex is going to be reflected over that line, right? And its x and y coordinates are going to get switched also. So it's going to become kh, right? Does that make sense? And so we end up then with that, right? Make sense? Okay, so really either way works the same, horizontal or vertical. Okay, so let's look at a couple problems. I want to start with, let's go back and look at a couple circle problems. So these are the kinds of things it looked like people were having some trouble with. Okay, so let's write this circle. Let's go back to circles for a second. Because now, remember, if we write up the standard form equation of a circle, doesn't that look awfully similar to a parabola? Right? What was the standard form equation of a circle? This was parabola.
X squared plus y squared equals
Okay, let's do circle. What was the circle, remember?
x squared plus y squared equals
X squared plus y squared equals r squared would be if it's centered on the origin, right? But if it's centered on the point HK, really all we were doing, right, if it was centered on the point HK, so that's the center of the circle, and that's the point XY, is saying that that's equal to R. Right? That's it. That defines our circle. What's the locus of points for a circle? It's the locus of points equidistant from the center, right? So all we have to do is say that the distance between the variable point XY and the center, HK, is equal to some constant, which we're going to label the radius, call it R, right? And so what do we get then? Well, by Pythagorean theorem or the distance formula, we just get this distance, which is, that distance right there, the difference in the x coordinates is x minus h squared, right? And the difference in the y coordinates is y minus k squared, right?
Ooh, did you guys win?
Equals r squared, right? That make sense? So there's a circle, there's a parabola. They look pretty similar, don't they? Right? So let's go back to this problem then. So
Wait, it didn't.
there. So we got to put that into. This is a circle, right? So we've got to put this into the form x minus h squared plus y minus k squared equals r squared. How do we do that? Okay, good. Okay, yeah. Let's go through this. So we're going to complete the square for the x terms and complete the square for the y terms, so we can get something like x minus h quantity squared and y minus k quantity squared, right? So let's take these guys. Let's kind of color code this here. We'll take the x terms and we'll leave a space, right? Plus, let's do the y terms. And then let's chase the constant over to the other side, right? And all we got to do is just add the appropriate blue number and red number to both sides to create perfect squares, right? That's it. So what's going to be, let's look at the blue numbers. So what am I going to end up with down here? What's my perfect square going to be? In other words, what's h?
X plus 1.
1. Good. So h is what then?
Negative 1.
Negative 1, right? Because it's x minus negative 1, right? So to get that, what did I have to add to both sides?
1.
1. I had to add half of b, which is 1, squared. Okay? What about right here? I'm going to get y plus, or y minus what? 9. Okay, so then k is 9. And I add to both sides?
81.
81. Okay, so what's that give me on this side then? I'm going to get 82 minus 18 is 72, 64. Right? Done. That's it. Okay, that's in standard form, isn't it? Right? We can see from this form that this is a circle centered on HK equals negative 1, 9 with a radius of what?
60.
No,
Just kidding, 8.
8. There you go. Okay, because that's r squared. Okay? Make sense? Okay. So what about, let's take one like that, but maybe for parabolas. Okay, how about one like that? Okay, what am I gonna do with this one? Now, is this gonna be a horizontal or a vertical parabola? What do you think? Horizontal or vertical? Think about the two. If we go back to our, here, let's write them down. So we've got a vertical parabola is gonna fit the form what? Remember that one? X minus h squared equals 4p times y minus k. And then we're just gonna flip around the x minus h's and y minus k's, right, to make this horizontal. Okay, that makes sense, doesn't it? Because think about a regular, if you're ever not sure, just think about the parent function for a vertical parabola, right? Think about that. So one centered on the origin. What's the equation of our everyday parent parabola? Y equals x squared, right? Well, which one would that fit? If k was 0 and h was 0 and p was 1/4, right? Then we would just get y equals x squared, right? So when the x's are being squared, that must be the one that's the vertical parabola, right? Okay? So that's what we got here, isn't it? So what am I going to do with this? If I want to put this into standard form. Okay, so yeah, I'm gonna do something like, let's put the x terms on the left side, right? So I'm gonna get x squared minus 10x, leave a space, equals, and then on the other side, let's just put the y term and the constant on the other side. Everybody agree? So we get positive 16y minus 41. Okay, what do we have to, now what? Okay, so we're gonna do, this side is gonna become x minus 5 squared, which means I have to add to both sides 25. Okay, so that's good. We got the right side all squared away. On the left side, we've got 16y negative 41 plus 25 is what? Negative 16. So what can I do to the right side then to get it to look like this? What do you think? What am I going to do? Okay, I could factor out a 4, right? And I can see that I want to have, inside the parentheses, I need to have y minus something. So I could maybe even go one step further than that. If I want the y to be by itself inside the factor,
Divided by 16.
I've got to factor out a 16. Whatever the coefficient of y is, I've got to factor that out, don't I? Right? So that's going to give me 16 times what? If I undistribute or divide away a 16, what's the first term leave me with? What's the second term leave me with? Okay? Right? And so it's in standard form then, isn't it? Right? Now we could write this if we wanted to as 4 times 4, but that's okay. If we wanted to, this is fine, like this. I'll show you why. If we leave it like that, the question is, can we look at this and extract the values of h and k and p? We can, can't we? Right? What's hk? The vertex of the parabola is at what? 5, 1. And what's the distance between the focus and the vertex? P. Yeah, P is just, if 4P is equal to 16, it's just that number divided by 4, isn't it? Right? That's all we need. That information defines the parabola, right? Okay, does that make sense? This tells us where the vertex is and how far away the vertex is from the focus, which just means that point, doesn't it? That point and that distance. Right, if I change this point a little bit, see if I can do that. Yeah, it's gonna change the parabola, isn't it? Right? Okay. And if I change that distance, if I leave the point there, it changes the parabola. Okay, but I still get a parabola. That make sense? Okay. How we doing? 5 minutes. Oh, perfect time. Okay, so who wants to be